Hello and welcome to SW. My name is Eileen Fries.
My name is Manuel Scheibler.
And I'm here today to interview Manuel and find out about the SW solution for compressor wheels. Manuel, why are we looking at compressor wheels? What makes them important workpieces?
Well, for starters, it's a really interesting process. The turbocharger increases the efficiency for combustion engines. In the near future, they'll be produced in high quantities.
In naher Zukunft noch zahlreich verbaut werden.
Are we talking in terms of electric vehicles or just because we need more cars?
We need them primarily for more efficient combustion engines. But when it comes to hybrid cars, we'll also need compressor wheels and turbochargers at the ready.
Okay. It looks like you brought some different compressor wheels. Maybe you can explain the differences? Of course, we can see that there are some different sizes here, but are there any other specific details you can give us?
Yes, of course. One way they differentiate is by the type of material. For example, aluminum is mainly used in car applications. Here, we see a compressor wheel for a car. There's also titanium, which is mostly used for commercial vehicles or in racing. For example, here we see an aluminum wheel that would be used for commercial vehicles when it's constructed in this size.
Hier sehen wir zum Beispiel allerdings ein Aluminiumrad für den Nutzfahrzeugbereich, ja, in dieser Baugröße.
What are the characteristics of the blades? We can see that they've been formed differently. What makes this important for each wheel?
Exactly. Here we see two similar parts, but they're still different because they've been milled differently. Here, for example, the component underwent a flank milling process, which means the tool works like a shovel. The full length of the cutting edge is used to shoulder mill the blade. Generally, the machining time for this is short. Here we have a workpiece that's point milled, which means that I line the blade over only the tooltip in multiple paths. This machining process is much longer, but I can create much more complex contours, such as concave or convex blades.
Die Bearbeitungszeit ist hier deutlich länger, aber ich kann eben auch komplexere Konturen wie hier konkave, konvexe Schaufelblätter erstellen zum Beispiel.
What about this workpiece? It looks totally different, and I assume that's how the part arrives. Where did it come from, and how is it clamped?
Generally, you're going to start with a saw cut of an extruded profile or a forged component. It comes from the lathe like that, with the outer contour finished and turned. The center bore here is also finished by the time it makes it to the machining center.
Das heißt, die Außenkontur wird fertig gedreht und ebenfalls die Mittelbohrung hier ist bereits fertig bearbeitet, wenn es zu uns ans BAZ kommt.
Okay. Okay, and now can you tell us a little more about the clamping system? How do we grip it? Because there don't seem to be many possibilities for these workpieces. As you can see, it has to be processed like this. Look how flat it is on the bottom.
Yes, you have to be able to access the part from all angles.
Somehow you've got to be able to reach all the corners with simultaneous 5-axis milling.
Exactly. Like you said, it's processed with simultaneous 5-axis milling. This means that we have all machining axes in action at once. The part is clamped perfectly centered on the 5th axis table, so I put it on the fixture here on the back face, so to speak, and press down here on the wheel nose. It's centered via the bore in the middle, so it can go around the center bore axis.
Okay, when the workpiece is finished, how do we measure its values?
We have a 3D scanner in our measuring lab. That's where we scan the piece in 3D and we essentially get a 3D model that looks almost like this, but with the colors just a bit different. You can then easily make assessments and evaluate whether any corrections need to be made. Yeah, it's pretty cool.
Sehr schnell beurteilen, auswerten, wie hier Korrekturen einzubringen sind. Ja.
It could be frustrating given how complex it is, and especially if you're talking about a concave surface. It would be really difficult to try and map it in 2D if you had to.
And you can use different reference systems, so you can compare the milling contour and how it relates to the pre-turned part. Or you just look at the milling contour itself. There are really many possibilities.
Very true. Okay, now with a workpiece like this, there are bound to be some steep geometry challenges. How do SW Solutions manage to solve these?
Precision needs stability, and we have that covered like no one else. It's fundamental to our design principles with the monoblock at the core. This machine structure gives us stability, rigidity, and high accuracy even by the influence of temperature variation. On the other hand, we have the double swivel carrier in the two-table variant for loading and unloading in parallel to machining time.
Den Doppelschwenkträger in der Zweiplatz-Variante für das Hauptzeitparallele B- und Entladen.
We also have the machine as a single table variant, which means that the loading and unloading are factored into the processing time.
When would it make sense to go with a single table variant? Is it a question of price? Of course, it's less efficient, but are there components where this maybe isn't such a big deal? When might that be the case?
When you're working with larger wheels, for example, point milled wheels with long processing times, or titanium wheels with even longer processing times, of course, it makes sense to go for the single table variant. It's more cost effective when the loading and unloading times aren't a big factor.
Maschine und der Einfluss der B-Entladezeit des Werkstückwechsels ist verhältnismäßig gering.
How do we achieve dynamic machining with our spindles? Is this also a part of our design principles? Is there any other concept that comes to mind? Maybe you could briefly explain it to us.
Depending on the component and material, we have different spindles to choose from. The faster spindle for the WO2 is the HSK E40 with up to 36,000 revolutions per minute. For titanium machining, I would probably recommend the BA321 single table machine with an HSK 63 spindle with a maximum of about 17,500 RPM.
A63 Spindel mit maximal bis zu 17.500 Umdrehungen.
What does that look like in terms of productive and non-productive times for this workpiece?
This kind of component is inherently going to have a high proportion of productive time compared to non-productive time. The actual milling process takes up most of the time, which is why we focus so heavily on it and on the highest machine dynamics.
Deshalb legen wir hier ganz klar den Fokus auf den Fräsprozess und die höchste Dynamik der Maschine.
Okay, and the machine behind us? The reason we're standing here is the BAW022i. What's a good example of a good workpiece to exemplify how a process or how this machine would be a good solution for our customers?
On the one hand, the machine is perfectly suited for compressor wheels made for passenger cars, smaller compressor wheels, in addition to simple compressor wheels with a short cycle time. We have the double swivel carrier with minimum tool change times. The way the WO2 was developed, it's fundamentally prepared for 5-axis simultaneous machining. That means it has the highest acceleration and jerk values that really can't be beat. You really can't get any faster than the WO2.
Entwickelt worden, das heißt, wir haben wirklich höchste Beschleunigungs- und Ruckwerte. Und da kommt man an der W02 einfach nicht vorbei. Schneller als auf der W02 geht's nicht.
And as you can see, we also have a yellow element, which doesn't normally belong with the SW colors, but it's there in the loading area. What's that about?
Yeah, we made an exception for this yellow Fanic robot. It takes over the loading and unloading during machining time. It's for these workpieces in the pallet storage attached to the side here. We can store up to 24 pallets here with smaller wheels. For example, about 48 components per pallet would result in about 1,152 pieces. If you factor in a 1-minute cycle time for such a component, we'd end up with more than 19 hours of unmanned production.
1152 Stück circa. Wenn man da wieder weiterrechnet, bei 1 Minute Taktzeit für so ein Rad, liegen wir bei ca. 19 Stunden, über 19 Stunden mannloser Fertigung.
That's a lot of time that someone could use for other processes. What kind of solution is there for titanium workpieces? Is there anything to keep in mind?
For titanium machining, the single table variant is the better choice. It's more cost effective. The tool change times don't have a big impact, so we'd go for the BA321. It's one of our very powerful ball screw drive machines, which is nevertheless very, very, very dynamic. And that would definitely make it the right choice, especially because loading and unloading has very little influence on the overall productive time.
Die trotzdem sehr, sehr, sehr dynamisch ist. Und das wäre definitiv die richtige Wahl. Hier hat einfach die B-Entladezeit einen geringen Einfluss auf die Gesamtlaufzeit des Bauteils.
Now seems like a good time to mention that the machine here is a linear motor machine, but SW still has the typical ball screw motors available. I'd like to bring up our motto, We Think Systems. What can you tell our viewers about that as a wrap-up?
We Think Systems, also wir denken in Fertigungssystemen. Was kannst du dazu noch sagen für unsere Zuschauer zum Mitnehmen als letztes
As you said, we think systems. Of course, it would be possible to create an entire process chain in an interleaking solution together with turning. The machine variant would look a bit different. Instead of a pallet storage, a workpiece feed belt would be attached, which would then be loaded with the pre-turned rounds by the robot automation and brought to the machine.
Werkstück-Zuführband quasi anbringen, das dann per Roboterautomation mit den vorgedrehten Runden bestückt wird und an die Maschine gebracht wird.
Maybe you could also mention the other functions that could be integrated into this standard loading cell?
We also have the possibility to DMC scan workpieces here in this small cell or to include workpiece labeling. There are so many different possibilities here, so you really should reach out and just talk to us.
Hier gibt's wirklich verschiedene Möglichkeiten, also sprechen Sie uns an. Ja?
Exactly. We're really flexible there. We're not just a machine manufacturer anymore. We're system solution suppliers, and we'd love to take a look at your workpiece and find your perfect solution. Send us an email. We look forward to hearing from you, and we hope you enjoyed our little interview. Thanks, Manuel.